So the next topic, calculating limits algebraically. As I previously said, calculating limits numerically and graphically, when we calculate limits numerically and graphically, the result is always approximate. It's never precise. Well, we just guess, so it may be exactly 12, it may be 12.005. For many practical reasons it's okay, but in mathematics we always try to obtain precise value of the limit, if possible. And for that reason, the numerical method and the graphical method of calculating limits are not very good. So there is a much better method, which is calculating limits algebraically. And now I want to show you how to calculate limits using this algebraic method. Very often, in fact, it's even much faster than numerical, so you don't need to plug in so many numbers in the function, and you will come up with an answer which is precise and not approximate. So here's an example. This is a simple example. Limit as x approaches 2, x squared minus 3x plus 7. So, of course we can do this limit, this example numerically as well, and for that, as you remember, we need to plug in numbers like 2.1 and 2.01, etc., and also 1.9 and 1.29, etc. So, and then we will come up with a certain answer. But actually we can do it in a much simpler way, like this. So here is the idea. When x approaches 2, which means when x takes values close to 2, x squared will approach 2 squared, which is 4. And 3x will approach 3 times 2, which is 6. And so the whole thing x squared minus 3x plus 7 will approach 2 squared minus 3 times 2 plus 7, which is what? 4 minus 6, negative 2 plus 7 is 5, and here we are. So this is the value of the limit. Now I told you that you're supposed to plug in numbers like that. I didn't really plug in any numbers like that, 2.1 and 2.01. In fact, what I have done, I just plugged in exactly 2. For x. So this is what I have done. So I just plug in x equals 2, whatever the value x approaches, and plug in purely algebraic operation, and the answer is 2 squared minus 3 times 2 plus 7, which is 5, and that is the way of calculating limits. So just plug in. So in short, this idea can be described with 2 letters, with 2 words or 3 words, just plug in. Very simple idea. Now you may wonder, why do we not use this method all the time? Because so simple method, we don't need to bother with numbers like 1.9 and 2.01, etc. So this is very simple way. Just plug in and get the answer. It is of course algebraic, but that it is so simple, so why don't we use it all the time? Why do we bother with graphs, with the numerical method, with using numbers like 1.9, etc.? The reason why is because unfortunately this simple method of plug-in or substitution is not working. So unfortunately this method, oftentimes this method is not working. And to show you one example in which it's not working, I want to come back to one of the examples that we have already done numerically. So let me write what I just said. So unfortunately, we just plug in is often not working. And here's one example, same as before. Limit as x approaches 2, x cubed minus 8 divided by x minus 2. So to calculate this limit, we can of course do it numerically. We have done it numerically, but now I want to use this method. Just plug in. And I want to show you that actually for this limit, that method is not working. If we do want to plug in, what do we plug in? Since x approaches 2, we want to plug in x equals 2, like we did in the previous example. But when we do, then you see what happens. So denominator equals 0. In fact, it's even worse. Numerator also equals 0. So what we got is 0 over 0. Now here you can see the difference between algebra and calculus. If we do an example in algebra or a problem in algebra, whenever there is division by 0, in algebra we say it's undefined, there is no answer. However, not so in calculus. This same example we did numerically, and we know the answer. The answer was 12. And that's how this 0 over 0, for this particular example, 0 divided by 0 equals 12. For a different example, 0 divided by 0 may equal something else. And so what I want to say, 0 over 0 in calculus, 0 over 0 does not mean undefined, or DNE. So let me write what I just said. So in calculus, 0 over 0 does not mean DNE or undefined. So what does it mean? Well, it actually means nothing. It just means that we need to do some kind of manipulations in order to be able to solve this. So what exactly manipulations do we want? Any algebraic manipulations, any algebraic factoring, anything. Like in this case I mentioned factoring. Yes, factoring actually works. If you look at the numerator here, x cubed minus 8, it can be factored. So use factoring. So specifically the numerator x cubed minus 8 can be factored. How? I remind you formula from algebra. Among many formulas there is this one, a cubed minus b cubed. And there is a formula for factoring this. It's a minus b times a squared plus ab plus b squared. Now this exactly matches the numerator of our limit, because if you say x, a is x and b is 2, then b cubed is 2 cubed, which is 8. And so a is x and b is 2. And using this substitution, so we can easily see that x cubed minus 8 can be factored as x minus 2 times x squared, because it's a squared plus ab will be 2x, and then b squared, because b is 2, so b squared is 4. So that's how we can factor the numerator. So now I want to erase this because I want to actually calculate this. So once again, plug in is no good, so I will erase this. And now I will put equal sign. Equal sign is already there. And I want to put equals limit x approaches 2. Once again, we know how to factor the numerator. It factors x minus 2 times x squared plus 2x plus 4. All of that over x minus 2. And now the next algebraic step or manipulation would be to cancel x minus 2 on the numerator and denominator. Actually, we have to be careful about cancellations like that, because in algebra we can cancel pretty much anything except 0. We cannot cancel 0. Therefore, we should make sure that whatever we are cancelling is not equal to 0. And in this case it's not. Why not? Because when x approaches 2, it means that x takes values close to 2, like 2.1 or like 1.9 again, but not quite exactly 2. Like we did plug in 2 to solve limit, but it was just a trick, so it's not really what limit is. So when we talk about limit, we don't really plug in exactly x equals 2, only close, like 2.1. And if we do plug in 2.1 or 2.01 or 1.9, so it will never be exactly 2. It will be close, but not quite exactly 0. So x minus 2 will be close to 0, but not quite exactly 0. Therefore, yes, we can cancel it. And now let's see what happens next. After we have cancelled, we will get just this part. So x squared plus 2x plus 4. And now we got a problem similar to previous example, which means in this problem, yes, we can plug in. Because there is, when we plug in, there is no situation like division by 0 or something, there is no division at all. And there are no other bad things that may occur. So we just plug in. So now we can plug in because no bad things occur. So plug in x equal 2 in this formula, and we get 2 squared plus 2 times 2 plus 4. So it's a 4 plus 4 plus 4, and the answer is 12. And this is the answer for the limit. Now this method is algebraic calculation. It's an example of algebraic calculation of the limit. You see the answer, of course, is the same as we previously got numerically, but it's actually better than that, because unlike numerical answer where we need to guess, is it 12 exactly or 12.005 or something, so it was always approximate. We never knew if that answer was precise. But now all these calculations are precise. So this answer is precise. And besides, if you know your algebra, if you know how to factor, how to cancel and everything, then this calculation is actually faster than numerical. You don't need a sophisticated calculator, you don't need to plug in. So this is the answer, and unlike in the numerical method when we plug in a lot of numbers, so now it's actually shorter method. As soon as you know your algebra, your algebraic manipulations, factoring and cancellation, it's actually shorter. And besides, this answer is precise. So now we can be 100% sure that this answer is exactly 12 and not 12.005. And that's why this method, whenever this method is available, it's always preferable in mathematics. So we always calculate limit, whenever possible, we calculate limits this way.